So I'm John Collomosse. I'm one of the academics here in the Centre for Vision, Speech and Signal Processing. I just want to take 10 minutes today to tell you about some of the new performance capture technology we've been developing here over the past few years. Compelling visuals and high quality character animation underpin many of the AAA games we see these days, and performance capture really drives a lot of that animation. We can see here a typical motion capture studio used to do that. It produces robust, high quality estimation of skeleton position. We've got limb joint estimations coming out of a system like this, but what we don't get from motion capture system like this is a capture of the surface, the dynamics of the surface, the skin, the muscle, the cloth as it moves, even the hair of the performer. And we don't get any visual appearance information either. We just simply get the joint angles. So what we've been working on is a new form of performance capture that captures all of that we call 4D performance capture. So we capture not only the skeleton and the joint angles, but we capture also a 3D mesh model that moves over time, okay, and captures those dynamics, the cloth, the hair, and also captures texture as well, so we can get a complete record, video realistic record of a performance. And even better, we don't need any markers to be worn, which is typically something that has to be done using existing motion capture technology. So this is just a sort of summary of our process. We have a studio, an actor walks in, and then through the video that's captured in that studio, a character model that's animatable walks out. And then, of course, you can do anything you like with that character model. You might do with a traditional games asset. You can insert it into scenes. Here we've got a piece of motion capture, just a jump, a walk, and a run that we've seamlessly blended together and concatenated to produce a piece of animation. There's a low hardware overhead in this kind of system. It's just video cameras and some software. So we think it could be quite an interesting thing to maybe put out there to the local industry to see if any independent studios interested in performance capture might be interested. So how does it work briefly? Well, as I say, we have a studio. A chroma key studio is what we use for best results, but in fact we can shoot against any background as long as it's distinctive in appearance against the actor. And what we do is we have 8 or more HD video cameras. They're calibrated through a process that I don't need to go into now, but it's pretty similar to standard mocap calibration with a wand. And then what we get for each video frame is a 3D mesh. Now those meshes are completely independent of one another. They don't have any alignment, and it makes them very difficult to use. So the key step really to make it usable in an animation context is to turn those independent 3D meshes that might have different topologies into a single 3D mesh that deforms over time. And of course that then captures the surface dynamics I was talking about, and it's trivial to get skeleton information, limb joint information out of that mesh just by rigging it with a skeleton. The model I've got here is just a low poly count, just a few thousand polys, but we can capture up to a few 100,000 polys with our system. So how do we do that crucial alignment step? Well, this is the kind of unstructured mesh information we get. What we do is we take a pose, typically a T pose like this, and align it to a few frames of our motion capture. We then align those frames to other frames and so on recursively to create a tree structure, and that structure allows us to track that mesh over time. And the result is, from the unstructured data, is a mesh that we can texture, perhaps with a static UV texture, as we've done here, just to show the coherence of the output. But as I'll go on to explain, we do something a bit more than that with the capture of the texture. So in this example, you can see a couple of models that have been captured, and we're able to then view them, of course, from any angle because they're 3D models. The way that we do this texture capture is we don't actually capture a single UV map, static texture map. Instead, what we do is texture the model at runtime by pulling pixels from the closest video, from the original source video we used to build the model, for the closest video to the user's point of view, what we call view-dependent rendering. And that allows us to capture view-dependent effects like specularities, and also fine details such as the wrinkles in the cloth that you wouldn't be able to get with a one-size-fits-all kind of static UV texture map. So moving on a little bit to how we can animate these models. We've got an example here of just some simple pieces of motion capture we captured in our studio. Here, a small jump and a large jump. Here, a short leap, a long leap, a walk and a run. And in each case, we are interpolating between those motions to create a smooth piece of animation. The little heartbeat thing here shows where we are in terms of the interpolation between, say, a high jump and a short jump. And of course, we can do that with texture. So with a few examples here, we can see a wide range of motions, all using our free viewpoint texturing process. So we've got the walk going to the run for all sorts of different speeds of motion and various sizes of jumps and so on. And this can all be done interactively in a real time, so it could be potentially useful in a game. In this example, it's a slightly more complex example. We have 5 types of motion: a run, a walk, a jump. I think there's a reach and one other. And what we can do here, and we've got a demo of this out in the expo in the foyer, is we can just interactively control this character in real time, just using a commodity PC and GPU. So it's a technology that could be potentially incorporated into a game, and one of the reasons we're showcasing it here today. In this other example, the same character, we've just got 2 pieces of motion capture, a bend to pick up a small object and a bend to pick up a large object. And again, we can interpolate between the two to allow the character to manipulate boxes of any size. And again, it's an interactive demo, so we're changing the size of the object here, and then the performance capture is being applied to animate the character. And you can see here at the side that we're not using a static texture for the character. We're pulling in pixels from these 8 source videos we use to generate the model to create this video realistic output. Okay, so it might sound like pulling pixels off videos at runtime to texture your model is really, really expensive and couldn't possibly work in a game. And initially, you would be right in saying that. However, we've developed a method of representing this data in an efficient way that doesn't cost any more really than just storing a bitmap for your textures. So instead of a single texture, we store 4 textures per video frame. We're able to then get an over 99% compression ratio on the representation. And looking at an example with and without that compression, it's very hard to tell any difference at all. You can still see the wrinkles in the cloth here, which are being captured by our dynamics of our surface, and the output is still video realistic. So our representation is so efficient that we can even deploy it on the web. So we've got a WebGL demo of this that you can check out at this URL here. And this came out of a collaboration we had with the BBC earlier this year, where we applied our technology to capture a ballet performance, and we allowed users to interactively explore the ballet on this BBC Taster website. One thing that we think is quite cool about our technology is that the meshes that we animate don't have any skeleton or rigging in them at all. They're just a set of meshes that we can interpolate between. But we also acknowledge that probably that's not a lot of use to the games industry that has skeletal animation embedded in its pipelines. So we've put a lot of effort into being able to drive our models using skeletal animation, using rigging. And these examples here show a single character that's been captured in our studio, but driven with a range of different motion capture examples that have been downloaded just off the web from the CMU mocap database. So just to summarize then, I've just outlined some technology we've developed here, this next generation performance capture pipeline that we've called 4D performance capture. Several kind of key points to it. First of all, it's a markerless technology, and that's important because if you consider, maybe you're shooting your next Doctor Who episode, or you're shooting, you're filming some Premier football game, perhaps then from the same footage you can extract a games asset for use for free from the same footage without any invasive marker placement. We've also sort of outlined that not only do you get the limb positions, the skeletal motion capture, but you also capture the surface dynamics and the appearance, and we can store all of that in a view-dependent rendering pipeline and representation that's efficient enough to work over a GPU and be deployed in a web browser. And we can control that model, that 4D model that we get, using either skeleton or no rigging at all, just interpolating the meshes. So far, we're very interested in seeing if we can incorporate this technology into games. We've tried incorporating it into the Unity engine with a bit of success, which is quite an interesting experiment. But we're certainly up for collaborating more on this. We've collaborated mainly so far with the broadcast and film post-production industries, but not with the games industry. And we hope that there's an opportunity through this event to maybe get some interest in that area. So as I say, we have a demo out in the foyer. We have a box on the feedback form that you can indicate if you'd like to follow up and maybe explore some of this technology with us. We'd love to. I'll be here, and many of the people who've contributed to the development of this technology are also going to be here this evening to talk to. If anyone's going to SIGGRAPH this year, we've also got a talk on this technology at SIGGRAPH 2015. Okay, so I'll hand over now to my colleague Kirk from Digital Media Arts to talk about some of his work in performance capture.